So this is our project, our final project, the Triton robot goalkeeper.
So the main description of our project is to implement a Triton robot goalkeeper that essentially prevents the ball from going past it. And this is essentially done in four or five basic steps, where we first localize the robot in a house room environment. Then we use computer vision techniques to detect the ball. Then we predict the trajectory of the ball using linear regression and velocity estimation, and then move the robot to the desired position to intercept the ball based on this.
So the first section of the project was localization within the house. So we use simultaneous localization and mapping using the Hector Slam ROS package. Um, why we selected Hector Slam was because it does not require an odometry topic in order to work, unlike something like G mapping. But it does generate a position estimate for the robot, as seen in the screenshot, which is important because we need a position of the robot in order to have a control loop for the robot's motion. Hector Slam, because it doesn't have an odometry estimate, it does have some trouble with a jerky robot moving. The map will get unaligned. So we sort of had to, account for that within our algorithm.
So the first step for computer vision, anyways, was pre-processing of the image. So first thing was going from BGR image, which is what uh, the computer vision package in Python uses, to HSV, which helps us find the ball. As you can see in that image, it does a mask of the image just based on different thresholds that we were able to find based on the lighting in the room, based on the color of the ball, where we can see just the ball in that image, as you can see after the mask, where the white represents the ball clearly and the black um, represents just the other space. And then after that, it came down to finding the ball within the 3D space relative to the robot. So first, we used that mask, found the ball within the image, which was that white area. And the largest white area is what we assumed would be the ball. And we would find the center of that area to be the center of the ball, which worked really fairly well. As you can see in that right image, the dot landed pretty much right on the ball. After that, it came down to using the intrinsic values of the camera, such as the focal length and the center pixel of the camera, to find the ball within three-dimensional space, using also the aligned depth data from the camera. After that, it was using the robot pose that came from the slam position uh, to find the ball relative to the robot, and then we could visualize that in RViz and start doing things with the actual finding the velocity, which we'll get to next. So as I was saying, now that we have the ball within that three-dimensional space, we can find its velocity and also its trajectory. We assumed that the ball was going to be moving just linear, which obviously is kind of a strong assumption. It just is the way we wanted to design it for just time constraints and stuff like that. But it actually did end up working pretty well. We'd roll the ball and then we'd determine the slope and the intercept of the regression line to find the ball's trajectory through space. And then we could extrapolate out from there and find where its heading direction was. So that way Liam could move on to finding that interception point.
So, in order to find the interception point, what we did is we found the closest point on that trajectory line, using just some math to determine which point on the line is closest to the robot. This works very well for this robot defending a goal area application because it means the robot is moving the least amount it needs to in order to intercept the ball, which was important because in such a real-time application, we just want the robot to be able to move the least amount it needs to in order to block the ball. This does have limitations because the robot, if the ball was moving too quickly and the closest point on the line was further than the robot could reach given its velocity constraints, it would not be able to reach it in time. But this in our testing for just the purposes of blocking the goal was not really an issue. And sort of the final piece was the robot motion control. So in order to control the motion of the robot, in order to intercept the ball, we used a P controller. It uses the robot's position received from the slam and then that interception point that's calculated from the line. The controller has a pretty low refresh rate in terms of granularity because the slam position updates fairly infrequently. So we just used a P loop instead of a full PID, and we just had a fairly large error band.
So after experimenting a bit, these are the kind of four main observations. So the first one was that the lighting conditions played an important role in performance, where the better the lighting, the better the performance. Then also another important part was the type of the ball actually significantly impacted the performance, where a solid like pink or like red colored ball worked best for like predicting the tracking and trajectory of the ball. And another thing was that it was kind of difficult for us to accurately predict the ball's path. So in order to do this, we kind of used two billiard sticks as a ramp so that the ball could be released in a linear or in a straight way. And the robot's environment also impacted the performance, where the fewer the obstacles there were in the environment, the more optimal the conditions were. So here are a few things we thought might work for the future. So firstly, from the design perspective, we thought maybe using a Kalman filter would be better to predict nonlinear motion of the ball. And we thought since we didn't use an odometry system, that could be useful as well to complement the SLAM and our control loop. And also a path planning algorithm, maybe like A star, could be used to avoid random objects and obstacles. And from the project perspective, we thought the maybe like accurately redirecting the ball towards specific targets could be something we could build upon what we currently have. And an example of this could probably be if a human releases a ball and the robot kind of gets to the ball and hits it towards another human. So this would kind of be like passing the ball in soccer. And further building upon this could be where the robot could actually intercept the ball, stop it, and then maybe move along with it. So this is actually an FSM or a finite state machine plan we built for one of these future perspectives. So the way it would work is where we would first localize the robot and then kind of find the first human who would release the ball. And once that's done, we would kind of calculate how to intercept the ball and then finally find the second human and do the same for that as well. And yeah, thanks. That's our project.